discuss the concept of Exergy destruction. But before we start, let's revise the concept of Exergy very fast. So if we have a system and this system is at a higher temperature and pressure than the surroundings or the environment at T naught and P naught, so we can have work from the interaction between the system and the environment by any method we want. Heat engine or cable and wire if there is a difference in the elevation. So even if our system is at lower pressure and temperature, also there can be exergy from the transfer of heat or other properties from the environment to the system. Okay, so for a closed system, we know the formulas, and also for the open system, the only difference that there will be in most of the cases or almost all the cases, we deal with the steady state. So the change of the properties by time is equal to 0, and also the change for the exergy by time is equal to 0, and from it the change in the exergy is equal to 0 for a steady state devices like turbine, nozzle, pressure, and so on. Also, another main difference between the closed system and the open system is the exergy transfer by mass. So it will be the exergy transfer by mass will be the mass multiplied by the exergy, which contains the enthalpy and the velocity or the elevation. So now for the exergy destroyed, if we have a system here at for example temperature 200 degrees centigrade, and the environment is at 25 degrees centigrade, so we know that there will be heat transfer out from the system. But during this heat transfer, the temperature of our system will decrease. So it will be exchanging heat until it reaches equilibrium with the environment. So it will be 200, then it will start, the temperature distribution will be something like this. Over time, it will decrease, and this is over the distance. So as the time goes on, the temperature will decrease, and as we go away from the system, we will reach the temperature of the environment. So here, if we want to calculate the exergy transfer by heat, it will be a variable temperature, and in some cases we can't integrate due to lack of information. So we simply expand our system. So we say that this is our new boundary for the system. Initially it was here, so we moved it a little bit further, so it reaches an equilibrium with our environment. So what is the benefit of this? It is basically now that there is no exergy transfer by heat. Instead, the exergy transfer by heat in this case is converted to Exergy destroyed. So because when we take the boundaries around the system and we make an Exergy balance, the Exergy transfer by heat, it is 1 minus T naught over the temperature of the boundary multiplied by the Q leaving that boundary. So the temperature of the environment should be given or whatever it is. And uh, in case of variable boundary temperature, we need to integrate this. But if it was constant, then we use it as it is in the question. So the most important thing is that if the boundary was close to the system, there will be in our Exergy balance heat transfer or Exergy transfer by heat. So now if we extended our boundary to that case, where the heat or the boundary or boundary will be at the same temperature as the environment. So this will be 1 minus T naught from the low over the boundary temperature, which is also in this case, it is T naught multiplied by 2. So this term is 1 and this whole term will be 0. So we will not have any Exergy transfer by heat. Instead, it will this term will appear as an increase in the Exergy destroyed because this heat we didn't utilize it because we are taking our boundary at the environment. So we didn't utilize this heat by anything. So now let's take a look at this example. I'll not solve it numerically all. If you want, you can try doing it by yourself, but I'll just explain the idea of the Exergy destruction in this question. So air, ideal gas, enters the nozzle steadily. We know that it is steady even if it's not mentioned in the question. We know that it is a steady device. So it is this is a nozzle. It is entering at 200 kilopascal and at 65 degrees centigrade with a velocity of 35 meter per second. And these devices we need always to see if he gave us the velocity or if we can find it because uh, the velocity or the kinetic energy will appear in the Exergy balance. So we need to be careful with it. So this is the entrance and the exit. It is 3295 kilopascal. And as you can see here, the velocity is 240 meter per second. So the nozzle increases the velocity and reduces the pressure, as we can see. So the pressure energy will be transferred to be or converted to kinetic energy. And we also have heat loss from the nozzle, so it's not adiabatic. The heat loss, it is 3 kilojoule per kilogram. And he gave us that the temperature of the surrounding, it is, so the nozzle is projecting heat to the surrounding at 17 degrees centigrade. What we need to find is the temperature of the outlet. And we want to find the Exergy destructed or destroyed. So since we are dealing with air, we need to know what formulas to use. Shall we use the table or for assuming variable specific heat, or we use the formulas for constant specific heat? In this case, since we don't have the T2, we can't assume constant specific heat because the specific heat will vary because the temperature of the fluid here is changing of the air. So if we have T2, then we take the average specific heat as the average temperature, but here T2 is unknown, so we can't do that. So the only option we have is to use or to assume variable specific heat. So we need to use the tables. This is point one. Point two, how to find T2. By making, so if we looked here at this question, the only way to find T2 is by using an energy balance from the thermodynamics, normal energy balance. So it will be the energy in minus the energy out will be equal to the change of the energy. And since we said that this is a steady device, it's a nozzle, so we can remove this and take it as 0. We'll take that energy entering the system is equal to the energy leaving. So what are the forms of energy entering the system? We have since this is an open system, so we have enthalpy and we have velocity. These are entering the system. Now what are the ones leaving the system? We have a Q, heat, and we have also the same enthalpy and velocity. So this will be the energy in. It is H1 plus V1 squared by 2 here. Since we said it's energy transferring into the system by mass, so initial or it should be like this: H1 plus half V1 squared. But here we are dealing with the specific form of the equation. So we remove this. We remove the mass, and this will equal to H2 plus V2 squared by 2 plus Q up. Now we are not given H1, so how to find it? Since we assumed variable specific heat, we can't use the equation for the enthalpy, which was delta H equal to Cp delta T. We don't know T2, so we can't use these equations either. And of course, we don't know the Cp. So the only choice is to find the H1 from the table using the T1 given to us. It is 65 degrees centigrade. So after we find the H1 from the T1, this will be known, this is known, this and this. So the only unknown is the only unknown left is the H2. So we rearrange the equation, will be H1 minus Q out, and we will combine these two together, the V1 and the V2, to simplify the converging. I'll show it now. V1 squared minus V2 squared divided by 2. Now this enthalpy we found from the table, it is kilojoule per kilogram. This is also given in kilojoule per kilogram, but this term here, it is in meter square per second square, which is equal to joule per kilogram. So we can't simply add them together. So we need to convert this term here into joule to the kilojoule per kilogram. And how to do this? We simply divide by 1000. So this term will be also kilojoule per kilogram. Now we can add them together and get the correct answer. And this is very important. Maybe you will face it many times in the exam, and you need to be careful with it. So now we found H2. So now from H2, we go to the table and found T2, the table A17, I think. So this is the first thing. Now the important thing about this question is the Exergy destroyed. So how to find it? As we know, there are two ways to find the Exergy destroyed. First, it is the T naught multiplied by the S generation, and the second way is from the entropy balance. Exergy in minus Exergy out minus Exergy destroyed. For steady devices, it is the change is equal to 0, as we mentioned. So directly you can find the Exergy destroyed from this term, or using the T naught S generation. Now both will give you the same answer if you do them correctly, but in some cases it will be some methods will be more complicated than others. So you need to know what are given to you, so you simplify things on yourself. Now let's see first this method because it's easier as the textbook did it first. Then we will solve it with the other method also, and we will see how to get the same answer. So now the Exergy destroyed, it is equal to T naught multiplied by the S generation. This term can be found from entropy balance. What is entropy balance? It is Sn minus S out plus the S generation. It is equal for steady devices. It is equal to 0. Not for a closed system. For a closed system, we will have delta S, but here it is steady device, so it will be 0. Now again, what is the entropy entering our system? It is an open system. We have mass flow rate in, mass flow rate out, and the Q out. So it will be M S1 minus M S2 minus Q out divided by the temperature of the boundary plus S generation. It is equal to 0. Here we will remove the mass because it's not given anyway in the question, and it's okay to find the Exergy destroyed as kilojoule per kilogram. Here, of course, there should be mass, then we remove it, the same thing here. So it's the same. Now S1 minus S2 for air. It's an ideal gas, and we are solving this problem using variable specific heat. So what is the formula for this case? The formula you should use, it is delta S is equal to S2 naught minus S1 naught minus R ln P2 minus P1. Now these two can be found directly from the table. At T2 we found it, and at T1 we found it also. Or of course at H1 or H2, the same thing. Now the R, it's from the tables. For air, the R it is 0.287, and the P2 and P1 both are given, so no need to worry about them. This is for the first term. Now the problem will be here, because we have the boundary temperature and the entropy, and unlike the Exergy, if this is our boundary temperature and it's not constant, as you can see from the question, it was at 65 degrees centigrade, then it will decrease as you move along the diffuser. So the boundary temperature is not constant. So if we expanded our boundary to include the immediate surrounding, then we'll have a Q out from the diffuser. But unlike the Exergy formula, this term will not be zero, because we need to account for the heat transfer inside our system, which will be converted into entropy generated inside our boundary. So usually this method is used, the expansion of the boundary is used to compensate or to include the total entropy generated in the heat transfer process. Because usually when we deal with Exergy, we want to make our system reach the environment. So if we took our boundary close to the system and the heat left, we don't know anything about it later. It will keep transferring in this immediate surrounding until it becomes zero heat transfer after the temperature decays to the environment temperature. So we don't know anything about this entropy here or exterior destruction happening here. So in order to calculate or to account for all this destruction happening, we will expand our boundary to be at the same temperature as the surroundings, which is in the question 17 degrees centigrade. Okay, so what the changes will be on the equation? We said that these terms from this equation. Now Q out will not change. The boundary temperature after we expanded this our system, it will be equal to the T naught. So from here we find the entropy generated, and it will be equal to S2 minus S1 plus the Q out divided by T naught in this case. Now, as you can see, the difference here for this case, the entropy generated, it is S2 minus S1 plus Q out over the boundary temperature, which is between the 65 degrees centigrade and the T2. And T2 will be, if you calculate it, it will be 34. So as we can see in both cases, the temperature is still higher than 17 degrees centigrade. So if we substitute the average, or if we integrate this term, here the temperature will be high. Okay, so this term will be low. So we will add a low value to this term. So at the end we will get a lower value than the case of taking the boundary and the immediate surrounding, because here the T naught, it is 17, which is lower than the initial boundary temperature. So we will add a higher value to this term, which will mean that the entropy generation will be higher. And this is, of course, makes sense, because the entropy generation inside our system will be happening at a larger area. So from this equation we find the S generation, and then we multiply it by T naught to get the Exergy destroyed, and the question here will be finished. So now this is the first way, which is finding the Exergy destroyed using T naught S generation. Now we will find it using the Exergy balance. But here you can see how simple the entropy balance was to find the S gene. So in some cases you will just try to do it using the S generation first. If there was something unknown in the question, or it was difficult, so you try the Exergy balance. But usually it will be good in the entropy balance. So now you can calculate the Exergy destroyed here, and you will get an answer. And if you use this one, you will get the same answer exactly for the same boundary condition. You can't find an answer using an extended boundary, then doing the Exergy balance on a smaller boundary and expect to get the same answer. This will be incorrect, of course. So now let's do the Exergy balance on the extended boundary also. So we have the Exergy transfer into the system minus the Exergy transfer out of the system minus the Exergy destroyed. For steady devices, again it is 0. The change is 0. Why it is 0? Because if you take it in the rate form, so what does the rate form mean? It means that we are taking the change in the Exergy with respect to time, which is dx by dt, and we know that for steady devices no property is changing with time, which means that the change in the Exergy, it is 0 with respect to time. So now we have flow in, flow out, and we have a Q out. For this case, for here, even if we extended the boundary, we will still have mass flow rate in and mass flow rate out, because we don't know the fluid from where it is coming and we don't know that, or it is not, because in practical, the extended boundary, it is just a few millimeters or centimeters from your system. But here for illustration, we just draw it a little bit further. But that doesn't mean that this massive flow rate is uh, is not crossing this boundary. So we will assume the properties here is the same as the properties of the mass crossing here for the air, because the properties of the air, of course, is different than the surroundings. So the properties of air will be assumed to be constant, and this is a negligible difference for the air. So what we will get from this, we have, of course, again, we will not write the mass, although it is an Exergy transfer by mass. So we will just remove it to keep it in the specific form. So this will be psi1. The 1 refers to the inlet and the 2 refers to the outlet. Minus psi2 minus the heat. We'll see what will happen now. The Exergy transfer by heat will be 1 minus T naught. This T naught is from the equation itself, over the temperature of the boundary multiplied by Q minus the Exergy destroyed is equal to 0. Now, in case of the extended boundary, the temperature of our boundary, it will be the same as the temperature of the surroundings, which will equal to 17 degrees centigrade. So in this case, as discussed earlier, this will be 1 minus T naught over T naught multiplied by Q out, which is 1 minus 17 over 17. Of course, we don't put 17 here. We put it in Kelvin, which will be the same. This will be 290. 1 minus 290 over 290. 290 divided by 290 will be 1, of course. So 1 minus 1 multiplied by Q out. This will be our Exergy transfer by heat, which is 0. So we can just remove this term from the beginning. And now we will find the Exergy destroyed directly from this equation, which will be psi1 minus psi2. So you can, of course, it's not very efficient to do it, but you can use h1 minus the h naught for this, and use here h2 minus h naught, etc., etc. But of course, this will waste your time. So we combine these two in one formula, and we use for the open system, it will be h1 minus h2 minus t naught s1 minus s naught plus v1 squared minus v2 squared divided by 2. This will equal the Exergy destroyed. Now, as you remember, this we find from the table of air at T1, and H2 we found it from the energy balance. And T2, T naught is given. S1 minus S naught. Now we found S2 minus S1, not S1 minus S2 from this formula. So whatever the answer you get here, this is S2 minus S1, because as you can see, the two coming first also here. So in case of S1 minus S2, the formula will be S1 dot minus S2 dot minus R ln P1 divided by P2. So you just flip this and flip this. So if it's S1 minus S2, it will be ln P1 over P2. The R is the same. Here also you change. So if you got S2 minus S1 from this equation, you just flip the sign of it. For example, if it was 0.17, then S1 minus S2 will be minus 0.17. Just so you don't calculate it again. And of course, this formula, it is for ideal gas air at variable specific heat only. So, and now this is known, and also this, but of course, as you remember, this is in joule per kilogram, and all of these are in kilojoule, of course, kilojoule per kilogram, because here the entropy it is kilojoule per kilogram Kelvin, and it is multiplied by Kelvin, so it is also in kilojoule per kilogram. So to convert this to kilojoule, we divide by 1000. So you will get the Exergy destroyed exactly as the first method. So you can pick whatever you find better. Now there is another idea, but for a closed system. I'll not solve it, just I find this idea in the book and I'll discuss it here. So it was a problem 847. You can solve it by your own, and if you need any help, don't hesitate to ask me. So also we had a closed system and a source here at 150 degrees centigrade. So there is heat transfer into our system. The system is closed. It was a piston cylinder. So no mass flow in or out. So also we will discuss only the Exergy destroyed. You can use T naught as generation, or you can use the Exergy balance. Of course, both will give you the same answer. Here we have the same problem. The first, we have two main issues. The first is that the temperature of our boundary, if we took it closed, it will be changing. So to exclude this and uh, make the heat transfer at constant temperature, we extend our boundaries a little bit. So it will be the same as the source temperature. Now this is the surrounding. This is the source. And this is our system. So the boundaries we will take, initially it was closed. So we will just expand it a little bit, because the heat transfer is taking place here. So the portion of the boundary here will be taken to be at the same temperature as the source. Because the heat transfer is operating at this boundary, so we'll take it as the same. Now, the only difference in this question will be, but before this, I think that I told you that we usually expand the boundary to account for all the Exergy destruction happening uh, in further area where heat transfer is taking place, because we need to calculate the Exergy destruction associated with this heat transfer. So if the boundary was closed to our system, Exergy is being destructed here and we don't know anything about it. So basically, after we expand our system to this side, now the Exergy being destroyed is inside our system and we can calculate it. So this is the idea, also the second idea for expanding the boundary. Now for the S generation, we know that we'll use the balance to find it, and then we will multiply it by T naught to find the Exergy destroyed. But here, in the formula, the entropy transfer by heat will be Q into the system over the temperature of the boundary, and the Q is taking place at boundary temperature equal to the source. Now, this we don't have any problem with it, but for the Exergy, it will be T naught from the equation over the boundary temperature. Here, the boundary temperature, unlike the previous question, it is not the same as T naught, so you can say T naught over the T boundary will equal to T naught, then take it as 1 and 1 minus 1 it is 0. So this is wrong, of course, because now our boundary temperature after expansion, we didn't expand to reach the immediate surrounding or uh, the environment temperature, which we will have 0 Exergy transfer by heat. But we expanded to reach the source, the temperature of the source. And of course, we did that because the heat is transferring from the source, so we need to see all the Exergy destroyed associated with this heat being transferred. So in this case, the immediate surroundings will not cause the boundary temperature to be as the same environment temperature. So this term will be 1 minus T naught over the temperature of the source. Here let it be 200 degrees centigrade. Of course, you add 273, and here it is 150. You add also 273. So as you can see, they are not the same. So you need, when you do in two methods, or of course in the exam you don't need to use the two methods, use only one. But if you need to compare, you can see that using the T-naught generation will give you the same answer, but in this case you need to include the Exergy transfer by heat, as I mentioned. This is, I think, everything you need for the Exergy destroyed. If anything is not clear, you can talk to me, of course, on WhatsApp or email or on Steam. So thank you and Assalamu alaikum.